look into the DER integration issues. So just to have a slight background on this DER integration issues, here let us assume that multiple inverters are connected to the common AC microgrid bus. And we should remember here, these inverters, they do not simply behave as parallel sources. Uh, because of the presence of grid impedance, so whatever we call it as weak grid, there will be coupling among these inverters. So because of this coupling, the dynamics of one inverter will always have impact on the performance of the other inverters. This we call it basically as an inverter-inverter interactions. So we visualize these kind of interactions as impedance interactions here. So instead of directly looking into inverter-inverter interactions, we went on with a basic level study. I mean to say, we first considered interactions among a grid-connected inverter as well as a weak grid impedance, which is very much reflecting in the figure shown in the slide, which is the equivalent circuit of a grid-tied inverter with current control. So here, with this, what we can say, whenever we talk about the impedance interaction from basic electrical point of view, we always remember the impedance interaction as a resonance, which is occurring between two passive elements. And the stability of this resonance depends on the damping offered by the passive circuit, right? Damping can be either positive or zero in case of passive circuits. So if damping is positive, system will oscillate. I mean, the system will decay with respect to time. And if damping is zero, system will oscillate. This is what we have seen in passive circuits. But this is not the scenario when we have power electronic dominated power system. So I mean to say, the impedance, if I see the impedance looking at, I mean, standing at this PCC in this equivalent circuit, it is no more just a passive impedance. So from the PCC of this equivalent circuit, we have inverter output impedance towards the left, which is no more a passive, and towards the right we have a passive grid impedance. Basically, we have considered V grid by considering short circuit ratio of less than 3, around 2 or 2.5. So in this study, we are looking for analyzing the interactions among inverter output impedance and grid impedance. Our main analysis will be on inverter output impedance, because grid impedance is basically the passive elements that are connected across the PCC. So the inverter impedance, whatever we are talking about here, from the PCC, if I look at the inverter impedance, it is very much dependent on the damping offered by its control loops. So in this study, like as we all know, if I consider a normal grid-tied inverter with current control, it will have a current control loop as well as PLL loop. And the inverter output impedance is very much dependent on these current control loops, because each control loop has its own time scale, which always has the possibility to shape the inverter output impedance with respect to time. So here we are basically looking into how the PLL, which is used for phase locked loop, which is used for grid synchronization, shapes the output impedance of the inverter. So in order to carry out this study, what we have done is we have considered two current control schemes. One is decoupled DQ frame control, which is very popularly used in most of the industrial inverters, and we call it as current controller 1. And second one is the alpha beta frame current controlled inverter, which we have just designated as current controller 2, because both the current control schemes have PLL for grid synchronization. But the impact that PLL creates on the output impedance of these two inverters are different. That's what I would like to highlight here. So what we did was we just modeled the impedance characteristics of the inverter with two different current control schemes, and we have projected it in terms of impedance plots. If we look at the top right corner, we have two figures for CC1 and CC2. And if you look at the figure B, that is basically the inverter output impedance when current controller 1 is considered. If you look at here, we can see the extended negative damping region, which is offered by PLL, and it is also the function of the bandwidth of the PLL. As and when I increase the bandwidth of the PLL, this negative damping offered by the PLL was increasing. But that was not the case with respect to the inverter operating with current controller 2. It was not that much dependent on PLL bandwidth, and it was almost settling at 10 hertz for different bandwidth. we can see the plots are plotted for three different bandwidths. One is 42 hertz, one is 165 hertz, and one is 305 hertz bandwidth. So as and when bandwidths are being increased, the current controller one has very large or extended negative damping. So this negative damping is as good as amplification. So whenever inverter impedance interacts with the grid impedance, this negative damping will obviously result in system instability. So after understanding how PLL has impact on the two different current controllers, we have just given you the overview of how this drawback of PLL creates interactions among inverter and the grid impedance, right? So in this top bottom corner, we have given the interaction profiles of both the current control schemes. If you look at the first figure, that is interaction of CC1 with grid impedance. Here, in both the graphs, we have represented impedance in terms of an eigenvalue. Like basically, there are two eigenvalues which are extracted from the impedance model. If any one of the eigenvalue interact with the grid admittance. Hello. If anyone,
Narendra, please go ahead.
yeah. If any one of the eigenvalue interacts with the grid admittance, we can see one of the eigenvalue is interacting somewhere around 283 hertz, which is almost closer to the PLL bandwidth that we have taken in the top graph, right? So, and at that impedance intersection point, if I look at the phase margin of the system, it was negative. So it means that inverter is interacting with the grid impedance. Basically, impedance interaction is happening here, and the system may go unstable or it may remain under harmonic oscillations depending on the damping offered by the system. But in case of the current controller 2, even though interaction was happening at 308 hertz, but there was sufficient phase margin and system was remaining stable. And same thing has been tested in the hardware platform. We had taken a 10 kVA inverter which has been connected to a weak microgrid. Inductance was calculated for a short circuit ratio of 2, and we can see the harmonic oscillations in PCC quantities, that is the voltages as well as current. And because of this impedance interactions, we can see the harmonics that are being injected into the grid. So I would like to conclude here, because of this impedance interaction, uh, grid is being polluted because of the injected harmonics resulting from the interaction. So then what would be the solution for this? So we have seen higher PLL bandwidth is causing this problem. So the straightaway solution would be just go on reducing the PLL bandwidth. Why, instead of unnecessarily using the bandwidth above 50 hertz. But when we do so, there is one feature of the inverter, that is what we call as low voltage ride through, which will be greatly affected. I mean to say, under low voltage ride through operations, we always expect a fast detection of grid voltage phase angle, which is done by the PLL again. So if we reduce the PLL bandwidth, we know bandwidth is always related with the response time of the PLL. So again, response time will become slower and it may impact the LVRT operations. So that's why we are not very much impressed with reducing the PLL bandwidth. So the other option would be going with active damping or passive damping solutions, where extra hardware circuitries are required, or you need to have some additional dissipative resistors to offer damping during the interactions. But again, that have cost issues. Like when we go for active damping, again we need to have extra hardware circuitry. I mean, you need to have sensors to sense capacitor currents or different things. And passive damping, it always imposes losses. So to overcome that, what we thought of was, we thought of going for a software solution where we can design or develop a compensator which can nullify the or counteract the impact that the PLL is creating, and shape the impedance such that there is no negative damping region. So that we could achieve, and we could test with the hardware as well. So we can, at the right side, we have shown the waveforms of the whatever after incorporating the compensator. We can see whenever we have compensator, and this was tested for almost 305 PLL bandwidth. Even with 305 bandwidth, we have seen there was no interaction observed, and there was no harmonic oscillations observed in the PCC quantity. So this was the first task that we carried out in this last 1 year session with the test bed. And this article has been communicated, and it is under first revision has been submitted. So looking into the second objective, Yeah, before looking into the problem, let us look into the system under study. We have shown it at the top right corner of the slide. So here we have considered IEEE 33 bus distribution network, which is simulated inside the RTDS, and the DFIG wind system has been connected at, it has been integrated through the PHIL experimentation, set up to one of the buses of the distribution system. And basically, we look into the fault rate through analysis of the system here. So to give a more clarity on problem that has been addressed in this work, see here we can see this 33B system has been connected to the utility grid after the volt DC transformer. So whenever a fault occurs in the system, there is always a sudden dip in stator voltage. So because of this dip in stator voltage, a DC component is observed in the stator flux. As a result, there will be abrupt increase in rotor induced voltages and currents, which can damage the rotor side converter. So apart from that, due to the fault induced voltage, over voltage, even DC link capacitors will get damaged. So these are the two problems that we are looking for here. So apart from the above problem, I would also like to remember that grid norms always demand for DFIG wind system to be intact with grid during fault and support grid voltage by injecting reactive power into the system. So this is what we call it as fault ride through. So in order to achieve this, there were earlier very conventional mechanisms such as crowbar protection was adopted. In this crowbar protection, what they used to do is the RSC of the DFIG wind system was protected by short circuiting the rotor. But one drawback of this method is DFIG, once rotor is short circuited, DFIG start behaving like an induction motor, and it starts absorbing the reactive power from the grid rather than supporting the grid by injecting the reactive power. So to overcome this drawback, instead of crowbar protection, fault current limiters are being proposed in this work. So that is what the solution that has been proposed here. So apart from that, this fault current limiter, whatever we have shown at the top bottom in rightmost bottom of the slide. So basically, it is a power electronic arrangement. Uh, uh, which can maintain the fault rate through performance of the DFIG system. So basically here this has to this fault, whatever the fault current limiting system or fault current limiter that we have provided, it has two objectives to look here. One is it should make sure that the PCC voltage is maintained. If PCC voltage is maintained, then it is very much sure that we can protect the DC link capacitors, and we can also protect the rotor side converter being damaged due to rotor induced voltages and currents. So with this objective, this current limiter will be switched depending upon the various circumstances that have been designed in the work. So whatever the algorithm that has been presented here, basically this algorithm is to detect the faults, fault current by comparing the instantaneous values of the current with the measured current with the threshold value. So that was the solution proposed here. So here we can see various waveforms that has been presented here. What we have done is what would be the scenario when if we don't use this fault current limiter, and what are all the literature suggested methods that are which are called as existing methods and proposed algorithms. So here you can see in the proposed waveforms, somehow we could see the improvement in the PCC voltage compared to stator voltage or PCC voltage compared to other topologies that have been compared here. So this was the second work that was taken. Coming to the third work, this is the ongoing work that has been that is still under work. So here the objective was, so when we have DC microgrid and AC microgrid clusters, so we use interlinking converters to integrate these AC as well as DC microgrids. So when we have multiple interlinking converters which have different ratings, power sharing is always a challenge. So the reason being, so we know that if you consider a DC microgrid itself, so here we have a PV which is being connected to the DC bus through converter, unidirectional DC-DC converter, and we have battery which is a which is connected to the DC bus through bidirectional DC-DC converter, and again the ultra capacitor. So basically, battery maintains the DC bus voltage here. So one thing I would like to say is the DC line resistance has a large impact on the voltage regulation, which is being done by the battery. So the basic or the very popular solution for this is using virtual impedance techniques, or regulate the bus voltage by means of some secondary control. So if what happens if same problem exists in the AC as well as DC line parameters where your interlinking converters are connected. So this again has to be this at the has not been addressed in the literature to the greater extent. So because people will assume that like line resistances between the AC bus and the interlinking converter are almost negligible. So what would be the problem when we neglect this is power sharing may not be equal, and there are probably, I mean, chances that circulating currents may flow, and it may damage the system. So considering this, the objective, so what we thought was like there are solutions that have been proposed, in the sense in order to overcome this drawback, they have some signal injection methods to identify the or to estimate the resistance or DC resistance or AC resistance. Instead of what we thought was, instead of identifying these resistances or determining these line resistances, why can't we estimate the drops? I mean, whatever the voltage drop that are being that are occurred due to because of this lane resistances. So with this thought, this like a unified control has been proposed here. So in this control, what we do is we, with the help of this global parameter, because in the AC bus frequency is the global parameter during utility mode, and DC bus DC voltage DC bus voltage is the global parameter. So the droop will happen between these two parameters. So therefore, in the utility connected mode, for every frequency and for a given rated DC voltage and power rating of the inverter, there is always a given DC voltage that will determine the droop characteristics of the inverter. So based on that, the voltage drop has been estimated using some algorithms. So this algorithm has been given here. So looking into the hardware prototype that has been considered, at the top left bottom corner, we can see like the three different interlinking converters have been considered, which are having different ratings. So with this proposed algorithm, we can the system stability has been shown with the help of eigenvalue plots, and also this algorithm has been tested for both islanded mode as well as utility connected mode.